Nuclear power currently provides 20% of our electricity, yet within 15 years, most of the UK's nuclear power stations would have reached the end of their operational life. In the 2007 Energy White Paper, the UK government suggested that to ignore nuclear power, which is claimed to be one of the currently more cost-effective low-carbon options, will be to risk failing to meet our long-term carbon reduction goal. However, although nuclear power has a zero carbon footprint, public perception is coloured by issues of safety, the radiotoxicity of its waste, its links to nuclear weapon proliferation, and concerns about its vulnerability to terrorism. An alternative source of nuclear power may be that afforded by the energy amplifier, known also as the accelerator-driven subcritical reactor, or ADSR, first suggested by Carlo Rubbia of CERN. The energy amplifier has the potential to fill the gap of carbon-free nuclear power stations with a potentially safe, cheap, and more sustainable form of nuclear power. To understand the energy amplifier, let's start by taking a look at a conventional nuclear reactor. Conventional nuclear reactors are based upon the spontaneous fission, or splitting, of uranium, or more precisely, of uranium-235 nuclei. A uranium atom is composed of a nucleus containing 92 protons and 143 neutrons, around which 92 electrons orbit. If uranium-235 nuclei are bombarded with neutrons, they split into roughly equal fragments, together with 2 or 3 fission neutrons and a large amount of energy. Once slowed down or moderated by collisions with light atoms, such as water molecules or carbon atoms in graphite, these fission neutrons then go on to split other uranium-235 nuclei, releasing more energy and more neutrons, and the process continues. This is known as a chain reaction. The result is an enormous amount of energy in the form of heat from a small amount of uranium. This heat can be used to produce steam to drive turbines and produce electricity. Within a nuclear reactor core, some fission neutrons are lost by absorption. But if at least one neutron per fission goes on to produce another fission, then the reactor is said to be critical, and the nuclear fission process is self-sustaining for as long as any uranium-235 fuel remains. For safe operation of the reactor, the fission process and the number of available fission neutrons must be carefully controlled throughout reactor operation, on the one hand to sustain the nuclear chain reaction, and on the other to keep it under control. This is done by lowering or raising neutron-absorbing control rods into the reactor core. If on average fewer than 1 neutron per fission go on to split more uranium-235 nuclei, the nuclear reaction is not self-sustaining. The chain reaction stops, and the fission processes will quickly die away. Such a reactor is said to be subcritical. However, it's possible to introduce the additional neutrons needed to sustain the nuclear reaction from an external source using an accelerator to generate the extra neutrons. When high-energy protons hit the nuclei of heavy metals, such as lead or mercury, each proton chips off, or spools, 20 or 30 neutrons. So, in principle, it's possible to use these spallation neutrons to drive a subcritical reactor by targeting a very high energy and intense proton beam at a heavy metal spallation target embedded within the subcritical reactor core. In this way, the chain reaction is maintained as long as the accelerator is injecting protons into the spallation target. And of course, a small percentage of the electrical power generated by the reactor, say 5%, can be used to power the accelerator. The elegance of the system is that if the accelerator is switched off, the chain reaction stops and the reactor is safe. However, no operational energy amplifier has yet been built. Several designs are currently under investigation in Europe, including Myra at Mol in Belgium and elsewhere in the world. Unfortunately, existing accelerators, such as cyclotrons, synchrotrons, and linear accelerators, cannot provide a proton beam of the stability and reliability demanded by the engineering constraints of the ADSR. An unstable beam leads to rapid heating and cooling cycles, which will severely challenge the integrity of the reactor core. The non-scaling FFAG accelerator could therefore be a key factor in making energy amplifiers viable by providing the stability and simplicity that is required from a proton driver. Moreover, because non-scaling FFAGs are likely to be significantly cheaper than any other equivalent accelerator, it may be possible to use several non-scaling FFAG drivers simultaneously. This modification would ensure against any accelerator instabilities, as it's unlikely that at any one time more than one accelerator would lose its beam. Economically, and for long-term sustainability, energy amplifier-generated electricity is highly desirable. It's possible to fuel an energy amplifier with natural thorium, which is 4 times more plentiful than uranium. Such a thorium-based system both breeds and burns its own fuel, and doesn't produce plutonium as part of the fuel cycle. Indeed, the radiotoxicity of nuclear waste from an energy amplifier is considerably lower than that from a conventional reactor. Additionally, the surplus neutrons produced by the spallation process can be utilized to burn, transmute, and render safe the waste from conventional reactors, reducing the length of time it takes for waste to become safe by a factor of 20. At present, there's very little research devoted to energy amplifiers. BASROC's CONFORM project will therefore not only help to bring the UK up to speed in this crucial technology, but will provide an innovative and cost-effective route to the proton drivers for energy amplifiers for the benefit of both the environment and the economy. And this is only the beginning. BASROC's CONFORM project is already exploring the application of non-scaling FFAG technology in many other fields of science. In years to come, we may see non-scaling FFAGs at the heart of many new science facilities, from muon sources for the study of fundamental properties of materials, through to major projects such as the proposed multi-billion-pound neutrino factory. The future for accelerator science and technology is clearly very bright.